All right. Hey, everyone, welcome. For this lecture, we're going to do exactly what the title says and catch up. Today, we're reviewing a few mathematical ideas that I'm going to assume that we have at least some familiarity with moving forward. Specifically, we're going to talk about fractions, exponents, and order of operations, which you probably remember as PEMDAS. Now, because this is a college math class, I'm not going to spend an hour reteaching every possible thing that you can do with fractions, right? This is more of a refresher. Some of this might be extremely familiar, and some of it might produce a feeling of like, yeah, I definitely remember learning this at some point in time, even if that was like 20 years ago. And some of you might see a fraction and immediately wonder what is going on. Why can't the numbers just do what numbers do? And that's okay. The goal here is to refresh the major ideas. We're going to look at a few examples and we're going to make sure that we have enough of a foundation moving forward. One thing that I want to emphasize, excuse me, throughout the course is that if you forget a rule, don't panic. Math usually gives us ways to reason our way back to what we need. So let's get started with fractions, right? And the first question here is, what is a fraction? Most of us learned, right, that fractions are part of a whole. And I want you to imagine you get a pizza, you cut it into 8 equal slices. And if I take one slice, I have 1/8 of the pizza, right? Like 1/8. And yes, pizza has probably done more work teaching fractions because everybody uses pizza or pie or something than anything else in mathematics. But fractions can represent so much more than just pieces of an object. They can also represent parts of a set. For example, let's say I have 15 students in a class and 3 students are absent, right? I can represent the absent students as 3 out of 15 or 3 over 15. That's how many students are absent. And I would also say 3/15. So the whole here isn't a physical object like one pizza. The whole is a set of 15 students. Fractions can also represent ratios, meaning relationships between different quantities. Maybe every 5 students requires 3 hours of tutoring, right? And we could describe the relationship as 3 hours for every 5 students. And that's a fraction, right? Or maybe even speed, right? If we say we were traveling 20 miles per hour, that's really 20 miles 1 hour, right? And another example would be if I go 150 miles in 3 hours, that would be 150 miles in 3 hours is a relationship between time and how far I've gone, right? That would equal 50 miles per hour. Fractions also show up when we're describing rates of change. So maybe Kwame grows 5 inches every year, right? Or our investment decreases by 20% every quarter, right? These are examples, right, where fractions are representing, right, a rate of change. When we're looking at fractions, we're comparing how something changes with another quantity. So when you see a fraction, don't automatically think pizza or pie, right? You can also think relationship. And a fraction is often telling us how one quantity relates to another quantity. Let's make sure that we have some of our vocabulary straight. The top number, right, of a fraction is the numerator, and the bottom number of a fraction is the denominator. If we have 1/8, the numerator is 1 and the denominator is 8. The numerator, the numerator tells us how many parts you have. while the denominator tells us how many parts there are altogether. So 1/8 means I have one part out of 8 total equal parts. And here's an important connection. A fraction is also division. That means 1/8 means exactly the same thing as 1 divided by 8. So if I want to convert a fraction into a decimal, I just divide the numerator by the denominator. So for example, 1/2, right, is really 1 divided by 2, which equals 0.5, right? It doesn't actually matter if we put the 0 first. 0.5 and 0.5 are the same thing, right? And the 0.5, right? We can write that in the same, in another way, right? We could also write it as 50%. So let's try another one. Let's try 3/4. If we have 3/4, that's the same thing as 3 divided by 4. It's the same thing as 0. And if you pulled out your calculator, you'd see it, 0.75, right? Or 75%, right? And those aren't 3 different numbers. They're 3 different representations of the same number. And that's an important idea in mathematics generally. Sometimes changing how a number is represented makes the problem much easier, right? Let's do one last quick example. If we had 5/4, this would be the same thing as 5 divided by 4, which would be the same thing as 1.25. And we could even write that as a percent. That would be 125%. We'll talk more later about changing decimals into percents, but the general idea is you just take the decimal point and you move it over 2 spaces to the right. So like here, 1, 2, and it becomes 75%, or here, 1, 2, we gotta add a 0, it becomes 50%, and here, 1, 2, and it becomes 125%, right? So in this last one, notice that there's nothing that says that our numerator has to be smaller than the denominator. If the numerator is larger, our fraction represents more than one whole. So 5/4 is the same as 1 1/4, or 1.25. All right, this is probably the section that causes the most trouble with fractions. Not because any one rule is incredibly difficult, but because different operations with fractions have different rules. Adding fractions works one way, multiplying works another way. Division says, you know what, let's flip something upside down and do something completely different, right? So let's organize this. When we are adding and subtracting fractions, the main thing is that we need the denominators to be the same. So in this scenario, if we have 2/5 and 3/5, we add them. The denominators are already the same, no problems. They already match. So we leave the denominator the same and we add the numerators, or the top numbers. So 2 plus 3 equals 5. So 2/5 plus 3/5 equals 5/5, which if we divide it, we get 1. So why do the denominators have to match? They have to match because the denominators tell us that the pieces are the same size. So if I have 2/5 and 3/5, I'm combining pieces that have the same size. It's like saying I have 2/4 and then someone gave me 3 more quarters and now I have 5/4. Easy, right? But what if I had something like 1/2 plus 1/4? Here, my pieces are different sizes. So I can't just add the tops and the bottoms and say, well, just add it and I get 2/6. No, that doesn't work, right? It would be very convenient. Unfortunately, mathematics has declined your request for convenience over everything. What we need here is a common denominator. So what's a denominator that both 2 and 4 can use? 4, because 1/2 is the same thing as 2/4, right? Essentially, a common denominator is a number where both of the denominators are factors of that number. And usually we want to try to find the smallest common denominator, which will make things the easiest. And here, the smallest number that both of these are factors of is 4, right? So 1/2 is the same thing as 2/4. And the 1/4 is already over 4. So we get 2/4 plus 1/4. The pieces are now the same size, and 2 plus 1 gives us 3. So this equals 3/4, right? It's the same thing with subtraction, right? So let's say we had, and I'll use a different color for this example. Let's say we had 5, 6 minus 2, 6. You're going to ask yourself, is the denominator the same? Yes, it is. It's both 6. So we can subtract, and 5 minus 2 equals 3. So that's 3/6, right? And here we can simplify this because, both of them, we can actually divide the 3 and the 6, and we get 1/2. So our answer is 1/2. And if we were subtracting and the denominators were not the same, we would actually do the exact same thing that we did with adding. We would need to find a common denominator. Multiplying fractions is probably easier. It's actually probably the easiest thing. When we multiply fractions, we just multiply straight across, right? The numerator times the numerator, denominator times the denominator. So here, right, we have 2/3 times 6/8, and we get 12/24. 2 times 6 equals 12. 3 times 8 equals 24. Let's say we had 3/4 times 2/5. 3 times 2 is 6. 4 times 5 is 20. So our answer is 6/20. We can simplify. We can divide both of these top numbers by 2, and we get 3/10. There's another thing that's really useful, right? About the word of when we're dealing with fractions. In many situations, of means multiplication. So if I ask you what is 3/4 of 2/5, I'm asking you to multiply those two fractions. So anytime you see of, it means multiplication, right? Now we have division. Dividing fractions has its own rule, right? Here it says flip the second fraction and multiply. Flipping the fraction gives you the reciprocal, right? That's the mathematical word for flipping a fraction. Another thing that we can remember is keep. Let's write it on the top. Keep, change, and flip, which tells us what to do to each one. We keep the first one, right? So that's 4/6. We keep it. Change the operation, divide it becomes multiplied by, and we flip the second one, 3/1. All right, and then we multiply across and we get 12/6. Very straightforward. The mathematical word again for flipping that fraction is called the reciprocal. That's the mathematical word for it. So keep, change, flip. You do this for any of the fractions that we're multiplying. It's the same in each of the scenarios, right? Now, let's say, right, let's do another example, right? Let's do, come over here. Let's do 2/3, right, divided by 1/4. 1/4. We keep the 2/3. We change the division to multiplication, and we flip the 1/4 to make it 4/1. So now we have 2/3 times 4/1, multiply across, and we get 8/3. 2 times 4 is 8, 3 times 1 is 3, and we get 8/3, right? Now, this is a mixed number, which is 2 and 2/3, because the 3, we get 3, a 3, and then 2/3 left over. So 2 and 2/3. Now, why does it make sense? Suppose I had 2/3 of a gallon of something, and each serving is 1/4 of a gallon. So I'm asking, how many 1/4 size portions can I get out of 2/3? The answer is 2 full portions and then 2 more thirds of a portion. So even though the rule feels a little strange, there's logic to it. Right? So the big fraction review here is to multiply, you multiply straight across. When we're adding and subtracting, make sure you have a common denominator first. And when we're dividing, multiply by the reciprocal. And whenever possible, you always want to simplify your answer, right? In the case of like mixed numbers, my preference is actually that you leave it as a mixed number. I'm sorry, we leave it as an improper fraction instead of a mixed number. Right? We want to work with the improper fractions and not the mixed numbers. All right, let's keep going. We're getting there. We're getting there. All right, so here with exponents, right? Exponents are essentially a shortcut for repeated multiplication, right? If we write 2 to the 3rd power, right? 2 to the 3rd power, the 2 is the base and the 3 is the exponent, right? Sometimes we call the exponent the power. The exponent tells us how many factors of the base we're multiplying together. So 2 cubed, or 2 to the 3rd power, means 2 times 2 times 2, which equals 8. One common mistake that you'll see is people multiplying the base and the exponent together. 2 cubed does not mean 2 times 3, which would be 6. 2 cubed means 2 times 2 times 2, which equals 8. Another example would be something like 5 squared, right? That would be what? 5 times 5, which equals 25, right? And let's say we had 5 cubed, or 5 to the 3rd power. And what I want you to do is just pause it real quick. Pause the video and try to do it yourself, and then play the video and see if you got it right, right? So give you 3 seconds, right? All right, let's see the answer. 5 cubed means we're doing 5 times 5 times 5, which equals 125. 5 times 5 is 25. 25 times 5 is 125. So when you see an exponent, mentally translate it as repeated multiplication. This becomes especially important when we get to the exponent rules. So here are our rules for exponents, right? In this slide, there are quite a few rules on it. I don't want you to stare at this slide for 30 seconds and then suddenly tattoo all of these onto your brain. Instead, let's look at some patterns, right? So for the first one, we have the easy ones. Anything raised to the 1st power is itself. It doesn't matter what it is, right? 100 raised to the 1st power is 100. 7 to the 1st power is 7. And 1 raised to any power is still 1. So 1 to the 5th is 1. 1 to the 500th power is still 1. You can multiply 1 by itself all day if you like. It's not going to change, right? 1 times 1 times 1 times 1 times 1 times 1 still equals 1. So the rules of 1 are very, very easy. Next, let's look at the product rule. If we're multiplying powers and we have the same base, that's very, very important. The base has to be the same. Then we add the exponents, right? So let's say we had 2 cubed times 2 squared, right? Let's check the base. The base is the same. So we're going to add the exponents. That becomes 2 to the 5th. And as you see in the example, we could actually break that down and say why. We could write it out. 2 cubed, right, is really 2 times 2 times 2. And 2 squared is 2 times 2. So what does this mean? 2 cubed times 2 squared is 2 times 2 times 2 times 2 times 2, right? This is this part, and then this is this part. And how many 2's do we have? We have 5 2's altogether, so it becomes 2 to the 5th, right? And this works with variables as well, right? X to the 4th times x cubed is going to be x to the 7th. X to the 4th times x cubed. Sometimes we'll use a dot, sometimes we'll use an x. In this class, primarily, we'll use a dot or we'll use a parentheses to represent multiplication. We don't really use the x because we're trying to like avoid the variable confusion. But here, the bases are the same, so we add the exponents. 4 plus 3 equals 7, so we get x to the 7th. The important thing here is the same base. If I have 2 cubed, right? Let's write it over here. If I have 2 cubed, right, times 3 squared, I can't just add these exponents because what? The bases, the bottom number is different. So I cannot do anything else with this. I could, do 2 cubed and then multiply it by 3 squared, but I can't add the exponents. All right, next we have the power rule. When a power is raised to another power, we multiply the exponents. For example, right, x squared raised x squared. All of this raised to the third power, right, just a little meter here, to the third power, right, we get x to the 6th. Now, the same way we wrote out this one, I'm actually going to challenge you all to write this one out on your own to see exactly why this becomes what it is, right? Write it out. Also, another example, if we had 2 cubed and we squared it all, right? That would equal 2 to the 6th, which equals 64, right? The quotient rule is the division version of the product rule. If we're dividing powers with the same base, again, the same base, we subtract the exponents. So x cubed, and here I'm going to use a slash for divided by x, I'm sorry, let's do it this way, x to the 8th divided by x cubed. The 8 minus 3 gives us 5, and that becomes x to the 5th, right? Or another example, if we had 3 to the 5th divided by 3 squared, the bases are the same, so we do 3 to 5 minus 2, and we get 3 cubed, which equals 27. Now for the zero rule, sometimes the zero rule feels like math is kind of playing games or playing tricks with you. But I promise you that's not what's happening. For the zero rule, any number that is not 0 raised to the 0th power equals 1. It doesn't matter what it is. So 8 to the 0 equals 1. 12 to the 0 equals 1. 5,742 to the 0 power, yeah, you guessed it, equals 1. The base cannot be 0, so it can't be 0 as the base, right? The base has to be something that's not 0. And when we do it, it equals 1. And finally, negative exponents. Negative exponents tell us to take the reciprocal and make the exponent positive. So it sounds like a lot, but it's really, really straightforward. So let's say we had 5 to the negative 2 power, right? We take the reciprocal, 1 over 5 to the negative 2. And then we make the exponent positive, right? So that becomes 1 over 5 squared. The exponent was negative 2. Now it becomes positive 2, right? And there we go. And 5 squared is 25, right? So 5 to the negative 2 equals 1 over 25. For any of these rules, right? And wait, real quick, I want you to pay attention to something here. A negative exponent doesn't mean that the answer is negative. 5 to the negative 2 power is not a negative 120, a negative 25 or anything like that. 5 to the negative 2 is positive 125th. The negative exponent does not mean that we're changing the sign. The negative exponent tells us something about the position of the base in a fraction. It doesn't attach the negative sign to the final number. So if you're reviewing these later, right, the big patterns that I want you to remember: when we're multiplying the same bases, add the exponents. When we're dividing the same bases, subtract the exponents. A power raised to a power, multiply the exponents, right? And with any of these rules, you always want to check and make sure that the bases are the same, right? We can't do it if the bases are not the same. All right, we're almost there. We're almost there. Now let's talk about PEMDAS. PEMDAS tells us order of operations. Excuse me, y'all. The reason we need this is that an expression can contain several different operations. And in mathematics, we need an agreed upon system for deciding what happens first. Otherwise, two people could take the exact same expression and get completely different answers, which, as we'll see on the next slide, the internet manages to do anyway. The P in PEMDAS stands for parentheses, right? The E stands for exponents, the M stands for multiplication, the D stands for division, the A stands for addition, the S stands for subtraction. I want to immediately correct one common misunderstanding. PEMDAS does not mean that multiplication always happens before division. And it does not mean addition always happens before subtraction. Multiplication and division are on the same level. You perform them from left to right in the order that they appear. Addition and subtraction are also on the same level. You perform them from left to right in the order that they appear. So a better way to think about PEMDAS is really 4 steps. First, we need to do groupings. That's the first one, all of the groupings. Second, we do the exponents. We're going to do all of the exponents. Then we multiply. Spelling stuff wrong here. Multiply or divide. Or divide is critical, from left to right. And then we add or subtract. from left to right. So let's do a few examples, right? Let's say we had 5 plus 3 times 2. We can go through the steps. If you work just from left to right, you might say 5 plus 3 is 8 times 2 is 16, but that would be incorrect because it's not the correct order. We're going to check. We don't have any groupings. We don't have any exponents, but we do have multiplication or division. So we're going to multiply first. That means we're going to do this first. 3 times 2 equals 6, and we have 5 plus 6. Then we can do the addition, and we get 11. Right? Now let's do another example. Let's say we had 5 plus 3 times 2. Move this last one. It's the same numbers, it's the same operations, but now we have a grouping. We have parentheses. And since we have the parentheses, the groupings, they go first. So now we have 5 plus 3 is going to happen first. 5 plus 3 is 8. Then we have multiplication. 8 times 2 equals 16. So parentheses can completely change the meaning of an expression. Let's do another one. Let's say we had 3 plus, let's do it more complicated. Let's say we had 3 plus 2 squared times 5, right? Let's go through our hierarchy. There's no parentheses, we're good. Exponents, we do have exponents, so we're going to do that first. 2 squared is 4. And then we're just going to rewrite everything else. 3 plus 4 times 5. And then here we have multiplication and division, so we're going to do that first. 4 times 5 is 20. And we have 3 plus 20, which equals 23. Now, here's what I really want you to remember, right? And it's because the left and the right thing sometimes becomes a little bit of an issue. Let's say, and I'll do this one in blue to make it more clear. Let's say we had 24, right? Divided by 6 times 2. Now, you might look at PEMDAS and say, oh, the M is before, sorry about that, y'all. The M is before the D. And since the M is before the D, you might say, oh, I'm going to multiply first. But no, remember, multiplication and division have equal priority, right? And what this means is that since they have equal priority, we do them in order from left to right. So we're going to do 24 divided by 6, and that is 4, times 2, and that becomes 8. So the correct answer is 8. Notice we did the division first. And the same thing happens with, let me find a place to do, we'll do it right here. Same thing happens with addition and subtraction, right? Let's say we had 10 minus 4 plus 2. Again, addition and subtraction are equal. So we're going to do them in order that they appear from left to right. 10 minus 4 is 6. 6 plus 2 is 8. There we go. Notice that we didn't do the 4 plus 2 first, because 4 plus 2 would be 6, and 10 minus 6 would be 4. That would not be the correct answer. One thing that's really, really easy to overlook is that the fraction bar creates groupings, right? So if I just write 6 plus 4 over 2, notice that everything in the denominator, how can we do this? Let's do red. Can we do red? Notice that everything in the denominator, it's a grouping. Let's not show it. Everything in the denominator is a grouping. So the 6 plus 4 is going to go first. And so this is going to be 6 plus 4, which is 10 divided by 2, which then equals 5, right? So that's very, very important. And the same thing applies if there's a complicated expression in the denominator. Treat the numerator as its own group, treat the denominator as its own group, and then you divide. So if you're ever looking at a problem and thinking, where do I even start? Don't try to solve the entire thing in your head. Just ask, what's the highest priority operation can I do right now? And do that one thing, rewrite the expression, and then ask the question again and go step by step. So now, a little bit ago, there was like a math problem on the internet, and everybody was getting it wrong. And you always see these pop up, right? And this is one of mathematics' greatest modern traditions, which is basically people arguing with other people, strangers on the internet, about what is basically elementary arithmetic. So here we have 8 divided by 2, and in parentheses, 2 times 2. So what I want you all to do is I want you to pause the video here and you try to solve it using the exact process that we discussed to see if you can get this answer correct. On the internet, a whole bunch of people getting this wrong because they don't, remember the PEMDAS that they learned, right? So pause the video, and in 3 seconds, I'm gonna go ahead and do it. Play it after you got your answer and see if you got it correct. All right, we're gonna do it now. So we start, since we have parentheses, we're going to do the exact process that we just discussed. We have parentheses, so we're going to do the parentheses first. 2 times 2 equals 4. And then we're going to rewrite all of what we just had. So now the expression becomes 8 divided by 2 times 4. Again, here's the key. Remember what we just talked about. Multiplication and division have the same priority. So from left to right for multiplication and division, because this is division, this is multiplication, right? When there's a single number inside of the parentheses, we don't have to do anything with that number. It just becomes regular multiplication. So since we're going from left to right, we're actually going to do this first. 8 divided by 2, which is 4. And then we have 4 times 4, which equals 16. So the answer that we get is 16, right? But this is the exact type of expression that causes arguments because the notation here isn't particularly good. Some people look at the 2 directly beside the parentheses and interpret that multiplication as being tightly attached to the parentheses. So like right here. And that's how people end up arguing for a different answer. The much better mathematical solution is to not create intentionally confusing notation in the first place. If I mean something like 8 divided by the entire quantity of 2 times 4, then I should use a fraction bar, right? So that would be 8 divided by 2 times 2 times 2. That's how I should write it. And then there's no confusion, right? If I mean 8 divided by 2, then multiplied by 2 times 2, I can also write that clearly. 8 divided by 2 times 2 times 2. This is much more clear as to what exactly we mean. So the real lesson from this viral and all of the other viral math problems is not really look how dumb everybody who got the answer wrong is. The real lesson is that good mathematical notation should communicate clearly. If your expression requires 400 comments on Facebook or Instagram or whatever, TikTok, right, to determine what you meant, maybe we can improve the expression. And that really is what PEMDAS gives us. It gives us a standard process, right, where if we're lost, we don't have to guess. We look for grouping, then we look for exponents, then we do multiplication and division from left to right. And then we do addition and subtraction from left to right. So, all right, that's our catch up. A few things that I want you to take away from this video, right? With fractions, remember that fractions represent relations and are also division problems. The numerator is on top, the denominator is on the bottom. right? Do we have a conclusion slide? Let's see. No, we don't. So we'll go right up to the top. Um, for fraction operations, if we're doing addition and subtraction, we need a common denominator. Multiplication goes straight across. And division, we multiply by the reciprocal. The reciprocal is flipping the fraction. The top number becomes the bottom number. The bottom number becomes the top number. With exponents, remember that they're shorthand for repeated multiplication. And when you're using exponent rules, pay attention to whether or not the bases are the same. And finally, with PEMDAS, think about it as 4 levels: grouping, then exponents, then multiplication and division from left to right, addition and subtraction from left to right. Most importantly, don't look at a long expression and try to solve everything all at once. Find the first thing that you're allowed to do that, and then repeat. Math becomes much more manageable when we're only asking ourselves to make one correct move at a time. So that's it for this review. Take notes, please. If you didn't take notes, go back in, write down the important stuff, right? Um, and make sure you're writing down the stuff, practicing, pause before examples, whatnot, right? Also, make sure you complete the homework assignment slash practice that goes along with this lecture. And I'll see you all in the next class. Enjoy your week.